All right, hello and welcome. We're going to be having a very brief video to start out with. This is in Chapter 10, Section 1, is vectors and the geometry of space. And when I say space, I mean three-dimensional space, so 3D space. And so section 1 is really just an introduction to that, the three-dimensional coordinate system. Because we can talk about things in space, but we want to be able to kind of quantify where they are. Oops. All right, so we're going to kind of look at in 2D the coordinate system that we're all kind of used to. Looks something like that. You have your x-axis and your y-axis, right? Now, and you would identify some point with like an x and a y coordinate. Maybe we would be better off giving it coordinates a and b, so as not to confuse with the x and the y kind of variable names, like coordinate names. But the idea is that, like, if you were to take this point and go straight down to the x-axis, you'd be at the value a, and if you were going to take this point and go over to the y-axis, you'd be at the value b, right? And we're going to sort of expand this visual kind of idea to a three-dimensional system by adding another variable, or another directional variable, which is the z variable. Now I'm going to draw this like this. This is typical. We have the x variable coming towards us, sort of, y over to the right, and z going up. Now I have this kind of diagonal just to emphasize the three-dimensional kind of nature of things. But so this point that I just drew before would be, if we were to illustrate the same point, it would be found here. Now this would be the point a comma b comma 0. If we were to now this point is on what we call the xy plane. Like if we were to kind of look at this flat surface that lives in 3D space, which is where we've been living for all of 2D kind of mathematics, that's the xy plane. It lives down there. It's like the floor. Now I'm going to illustrate the YZ plane, which is this one, which would be like the back wall. You see what I mean? This is where x is equal to 0. The YZ plane has z equal to 0, and then we have the XZ plane, which is going to be this 3D plane, and that's the plane where y equals 0. Okay, so before we had this point AB, but let's say we wanted to have a z component to it. So it doesn't live on the xy plane, but let's say it lives up here. So this is the point A comma B comma C, right? So the idea being, if we were to kind of, this might be the value C on the z-axis. To get to this point, we would go A units in the like along the x-axis. We would go B units along the y-axis direction, and then you'd go up C units along in the z direction. Like that takes us to this point ABC. And just as before, we kind of have this point on the xy plane, you could project this point onto the other axes. So I'm going to show you this point. It would map to, this is the point a comma 0 comma c on the xy plane, and then it would also project over to this point, which would be 0 comma b comma c. That's a point on the YZ plane that it projects to. We'll talk a little bit more about projections. These can be called orthogonal projections because like it makes a right angle, which if we drew them, they would look something like that. These right angles. But so you've got it. This is just our coordinate. Now, what I'm saying to you could be completely like obvious. This is how we talk about points in 3D space, but still, we want to formally describe it. So in notation, the space we're talking about we commonly call R3, and we use like a bold-faced R. In text, it's gonna like have little serifs and everything, but the R3 is going to be defined as the cross of, you take the real number line and then another real number line and then another real number line. So it's the real number line for each of the three components. This is one way of showing it with these x's, which are it's a set. It's a set operation, which we don't have to get into too much of the details, but this is just another way of representing it. It's all the points x, y, z, such that x, y, and z are all real numbers. Like this is another way of describing 3D space. It's just all points that are given three coordinates that are real number coordinates. So no complex numbers, but beyond that, everything's fair game. So let's see, a couple points to note. Any equation of x, y, and z can be represented as a surface in 3D space. For example, the surface, let's say x plus y plus z equals 1 would represent a plane. And we'll in later section of the book we'll be learning about all the different types of equations and how they represent different surfaces. Some of them are going to be curvy surfaces, some are going to be flat, some of them are going to be closed surfaces, some are going to be infinitely big. But any equation that you create that has x, y, and z in it the solution to this equation is a set of points in 3D space, and it's going to be a thin set of points. Like it's going to be like a membrane, a thin membrane. So I want to illustrate something else, the distance formula, how we get this in 3D space. Now I'm going to go back to this point. I'm going to show you this point A, B, C again, and remind you how we project this down to these values, A, B here. Now if I wanted to know how far this is from the origin point, what we can, using trigonometry, we can sort of figure this out by first getting the distance between the origin and this point, which would be A, B, 0. Because on the XY plane, that actually is that's actually a right triangle. It's kind of hard to see because it's slanted, but it basically looks like this. If we were to kind of flip it around a little bit, right? Where the height of the triangle has length b, and the base of it has length a. So as we know from the Pythagorean theorem, right, the hypotenuse of this is going to have length square root of a squared plus b squared. And so if we wanted to find this height of this triangle here is a height of c. And remember, it talked about like these projections are orthogonal, which is a word we're going to learn about later. Basically means a right angle. So this triangle, if we were to kind of flip it around a little bit, what we have is a height of c. We have a base that is square root of a squared plus b squared, right? That was the hypotenuse here. That's the base of this triangle that's like pointing up like a shark fin. And so by the Pythagorean theorem, right, the hypotenuse, let's call it this hypotenuse d squared equals the base squared, a squared plus b squared plus c squared, which is just a squared plus b squared, because the squaring and the square root cancel, and then what we get, d, is the square root of a squared plus b squared plus c squared. Now this is generally, we kind of generalize this to be the distance formula. The distance between 2 points, x1, y1, z1, and x2, y2, z2 is, and actually if I wanted to label these points P1 and P2, this is the way it's given in the book, can be written like this: P1, P2 with these little lines, which is kind of showing the norm or the length of such a line segment between them. But this is the formula. It's the square root of the difference in their coordinates squared, the sum of those squares. So x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That's the formula for distance in 3D space, which is just a kind of extension of distance in 2D space. And it should be noted, if you were going to abstract into 4D or 5D or higher dimensional space, the distance formula just kind of, the pattern just kind of continues to grow like that. We're not going to be dealing in 4D space in this course, but in some areas of math, you do have to go to higher dimensional space for modeling things with multiple variables. Anyway, this is basically it for the first section. We'll be going into much more. We'll be building on this with vectors and other stuff like that in later section. Okay, I'll see you then.